Today I'll tell you about some data about how remembering just one item can help us predict how well people can remember 5 items. And so I'll start by asking you to just do this task yourself. So first remember one color. And try to report where it was on the wheel. It was right there. Now try the same thing again, but with 5 colors instead. What color was right there? Something like that. And so many of you have probably done tasks like this before, and what I'll just assert that we already know about tasks like this is that performance will be worse with 5 items than with 1, and that some people will do better than others, that they'll have more working memory capacity. And so today what I want to talk about is why these are true and how they relate to each other. And as you know, there are many classes of theories that can explain why it is performance is limited in these conditions. Maybe the most well-known is the idea of item limits, that is that we can only remember, say, 3 or 4 items, and so of course performance is going to be better when we're below our capacity limit with 1 item than above our capacity limit with 5. Another class of model is resource models, which say that, when we have 1 item to remember, we can put all our resources in one bucket, but when we have 5, we have to split our resources among them. And another is interference, that is that when we hold 1 item in mind, it can have our whole attention, our whole visual cortex to itself, but when we have more than 1, they're going to suppress each other, interfere with each other, things like that. And of course these models can be very complicated, so I won't make any strong claims today, but I think individual differences naturally arise in different places in each of these theories. For example, item limits, usually people think the major source of individual variation is the number of items that can be remembered might vary between people. Resources, of course, the amount of resource would vary between people. And in interference theories, it's a little harder to nail down, but the most natural idea is not that people vary so much with remembering 1 item, but that the amount of interference varies between people. And so if you flush these out and what they predict about individual differences at set size 1 and set size 5, at least the very simplest prediction, of course there's lots of room for alternative views here, is that only 5 items is going to be a good measure of capacity, not 1 item, in an item limit view, because everybody can remember 1 item. That resources view suggests that 5 items and 1 item should both measure how many resources you have, because all the resources get used, but maybe with different sensitivity, right? Maybe set size 1 is hard to measure. And interference, I think, like item limits, suggests that 1 item really shouldn't tap into any interference, and so should not be as good a measure of capacity as 5 items, that there should be something special that gets added when you get to 5 items, or more than 1 at least. And so today what I want to do is show you some preliminary data where I measure performance from 1 item and 5 item tasks and look at their relationship. And I'll do this with 3 experiments that get sort of increasingly convincing of the point I'll make, and only the third will have control task. The data I'll show you is definitely preliminary, so I just want to start with that. That there's not a full story here yet, just interesting data that I think bears on how we should think about memory limits, and I'd welcome suggestions of all kinds. Okay, so first I'm going to show you a bunch of individual differences data, and so I wanted to just talk about a note about how you have to interpret individual differences data, because it's pretty subtle if you don't think about it usually. And one point there is that the reliability of each measure limits the possible correlation between them, right? So if you have a very poor measure of set size 1 performance that's not reliable, it couldn't possibly correlate well with set size 5. So what I'll do today is report the reliabilities of each measure before I show you the data, and then I'll report both the raw correlation between measures, say set size 1 and set size 5 performance, but also sort of a noise ceiling corrected measure. So I'll figure out the sort of maximum correlation given the reliabilities and adjust to that to allow you to interpret it with respect to the reliabilities as well. Okay, so let's get started. So the core issue at stake in trying to do this at all is how to measure performance for 1 item. Of course, there's many tasks we could give you with 1 item, say change detection, where this changes to green, where you would just be at ceiling, where everyone is at ceiling, and so you might think intuitively there's no great way to measure performance for set size 1. Lately, we've made a claim, maybe you know this already, that in fact, if you do, for example, a continuous reproduction task, you can use this to extract memory strength. That is, that continuous reproduction tasks don't really give us guess rates where there's no guesses here and some guesses here, and precision and variability and precision, but really just a single measure of strength that we can measure at both set size 5 and set size 1, effectively a signal to noise ratio, as I'll explain in a second. We can measure this with tasks that actually give us power to measure very high levels of performance like set size 1 and extract this memory strength that we quantify with d prime. And so the way this model works, in short, is to assume that before you see any items, all the colors feel equally familiar to you. When you see a color, like this green color over there, then it boosts familiarity for green, but also for very similar colors. And the shape of this function is basically fixed for all observers and all tasks. It's just a property of the color wheel, and we just measure it. And then during the delay, this activation boost that you got from encoding the item is corrupted by noise. There could be different amounts of noise, giving you ultimately, at the time you're tested, this distribution over how likely each color was to have been the color you saw. And if all you're asked is to report your strongest color, just which color was it, then you just report the maximum of this distribution. And in this model, you can predict the shape of error distributions such that if you have no signal at all and lots of noise, of course, which color is going to win, which is going to be the highest activation, is going to be totally random. And so you're going to end up with a uniform distribution. If you have a moderate amount of signal and a moderate amount of noise, about the same amount of signal and noise, then you're going to end up with a distribution like this, because of course the colors that get a boost from the signal are a little more likely to win, but any color could win if the noise happened to favor it. And so on all the way down to down here, where the signal is very large and the noise is very small, where the only colors that are ever going to win are going to be ones that got a big boost in the signal distribution. And effectively the claim of this model, and that we showed in this paper, is that all the error distributions always look like this. They look like this fixed function corrupted by different amounts of noise. And so we showed this, for example, here I'm plotting just the absolute value of error. We showed this for set size. So as set size goes up, all that you need to do is have the signal to noise ratio go down. When you increase the delay, the more noise accumulates conceivably, so this d prime value, the signal to noise value, goes down. When you increase the encoding time, conceivably the signal is going up and the same amount of noise is happening over the delay, and so you end up with a higher d prime, and so on. So our argument is that in any task, you can basically measure, for any set size, you can basically measure this d prime value, and this gives us a really sensitive measure of performance. And so this led us to asking, okay, well, if we look at different set sizes, how related are they? And so the first experiment I'll show you compares set size 1 and set size 5, like I foreshadowed, but because we were still a little worried about possibilities of sealing, we started by using an experiment where we made set size 1 harder. So we gave them only 100 milliseconds for set size 1, and then a mask, and then a 5-second delay. But at set size 5, we gave them a long encoding time, no mask, and a short delay. So the idea was to pull these a little closer together, and then ask how they're related. And then, given that data, we ask everyone to do both of those tasks. We can then take, say, their set size 1 data and fit the model to it and extract the d prime. We can take their set size 5 data for each subject and extract the d prime, and we can do that for all of our subjects. And then we can estimate the reliability with which we estimated those, in this case very high numbers, so very high reliabilities, only slightly limiting our correlation. And then we can plot those for each subject against each other. And what we get is something like this. So set size 1 d prime on this axis and set size 5 d prime on this axis. Naturally, people are better at set size 1 than 5, so these are below the diagonal. And the correlation is 0.78 here. And just totally coincidentally, that amounts to 78% of the explainable variance once you adjust for the reliability and do r squared. So this is a really strong relationship. That is, set size 5 performance is quite well predictable by set size 1 performance. And note that this really is about using this model. That is, if you tried to look at this in terms of like guess rate, you would find that down here there's lots of guesses, but over here there's none in either condition, for example, right? So breaking this into multiple measures can obscure this relationship, but once you realize there's this one unified measure, then you can observe this strong relationship. And so this is a pretty strong relationship, but I've also just always been suspicious that this might not be the best task, that continuous report isn't really a very good task, especially for set size 1. And that's because, to me, I have no data suggesting this. To me, it's always felt like set size 1 has some sort of like satisficing, some sort of sense that it's good enough. Like if you're sometimes asked to remember 5 things and you only know approximately the answer, but if you're then asked to remember 1 thing, you're tempted to just click in about the right spot. You don't try so hard to adjust it exactly. And this is, of course, going to severely compromise precise measurements of very high d primes, where we're talking about just tiny differences in errors. And so in our second experiment, we switched to a method that at least intuitively, felt like it would tap into these stronger, higher D primes better. So we made two changes. First, we got rid of all the masking and delay differences and the same exact encoding and delay and probe for 1 item and 5 items in this experiment. So exactly the same situation for both. And then we switched, instead of continuous report, they see an item and then they do a 4 alternative force choice task. And the way this 4AFC works, there's the target color, which you actually saw, and another choice is 12 degrees away from that target color, so a very tempting foil. And then the opposite color on the color wheel from the target, so 180 degrees away, and 112 degrees away from that. So if you never saw the target, all of these would look equally reasonable. But if you did see the target, there's a mix of sort of easy and hard distractors. And the way this works in the TCC model is fundamentally the same. You've still got the same signal to noise ratio, but instead of in color report where you're asking what the max is, here you're just saying, which of these 4 has the strongest signal, and that's how we model people's performance here. And so this gives us a lot of sensitivity, this task. As D prime changes in the model, this is simulations from the model, you predict that, of course, first, once D prime is sort of reasonable, they stop choosing the wrong color. So if they saw purple, they stop choosing yellow. But even up to very high D prime ranges, that other similar foil is going to still be tempting. And so there's sensitivity across this whole range to how strong their memory is in this task. And because there's only 4 choices on the screen, it's not so tempting for people to just say good enough. They know they need to know which of those 4 it was exactly. Okay, so when we do this task, we again get high reliabilities. We have 100 participants in this task. And again, we observe this very strong relationship between set size 1 D prime and set size 5 D prime. Now, of course, because we're not making set size 1 harder, the set size 1 D primes are much higher than the set size 5 D primes. And in terms of raw correlation, this is true, and overall this is about 82% of the explainable variance in set size 5 is predicted by set size 1 in this data. Okay, so of course there are strong correlations there. You can really predict a lot about set size 5 from set size 1. But some aspect of those strong correlations is just general, right? Some people are going to be more motivated, they're going to be better at all tasks. Basically any 2 tasks are going to positively correlate. Probably not 82% of the explainable variance, but to some extent. And so what we want is a control task. And the one we picked was mental rotation. So we asked people to say whether these rotate to be the same or whether they're mirrored. And we liked this task because it's extremely difficult, just like working memory tasks, dependent on visual processing, but minimally related to visual working memory capacity for colors. In fact, there are no colors in this task, so it's just another visually demanding task. And when we ran this experiment, here's what we found. So again, our reliabilities are high, a little bit lower, because we have a few less trials here. We ran more participants, so we have 171. I just ran this to the end of the semester. And here's what the data look like. Set size 1 and set size 5, so set size 1 on this axis and set size 5 on this axis, are extremely highly correlated. In fact, in this case, 97% of the explainable variance in set size 5 can be predicted from set size 1. Mental rotation on the y-axis here, by contrast, explained much less about set size 1 and set size 5, so 38 and 42% of the explainable variance. So there is definitely a main effect of people being good at these tasks in general, so 30 to 40% of the variance, but also a much stronger relationship between set size 1 and set size 5. Okay, so in summary, an individual set size 1 performance explains between 80 and 97% of the explainable variance in their set size 5 performance. And this is not totally domain general, at least. Set size 1 performance predicts much, much better than mental rotation. And just a nod that using this unified measure, this D prime measure, really allows this, which I think speaks to the value of this TCC model. Okay, so what does this mean about visual working memory? Well, I think it's most simple to explain in a resource model, right? In a model which, in general, I've been pretty skeptical of the idea that we have a single fixed pool of resources, but in general, that model makes this prediction straightforwardly, right? All of your resources get used for 1 item in one case, and they get split among for 5. Both are measures of how many resources you have. By contrast, this is pretty incompatible with an item limit model, right? You really shouldn't be able to measure working memory capacity at set size 1 if item limits are the critical factor explaining performance in set size 5. And it's harder to understand this data in an interference model because set size 1 has no interference. In fact, that's why set size 1 is such an interesting test case. But of course, I think there are many nuances that you could use to explain these. And I'm very open to your suggestions about how to test some of these ideas. Okay, thank you so much.